Our next section is logarithms to bases other than 10. So think about how we handled logarithms with base 10 numbers, and they will be related but slightly different. So we're going to determine values of logarithms in other bases. We're going to solve equations that are logarithms of other bases, and we're identifying and apply properties of logarithms. So it will seem a lot like what we previously did with base 10. So as you can see here, I've chosen to go with base 2 numbers. So our current equation, will go in pink, is our basic exponential, but it's not a base 10 problem, it's a base 2. So if we do like we did with base 10, and take a few positive, negative, and 0 values for x, we should be able to graph this thing, see what it looks like. And we should be expecting an exponential growth because our base value is bigger than 1. So if we do a -2, -1, 0, 1, and 2, put those in. If we start with the 2, 2 to the second is 4, 2 to the first power, 2, 2 to the 0 power, 1, 2 to the negative first is 1/2, and 2 to the negative second is 1/4. And again, reminder, we're not getting negative numbers, we're getting smaller and smaller fractions. So the farther we go into the negative numbers. Now, graphing this one, we're going to graphing it by as each of these are ones. And so in this dark red, we will graph 2, 4, 1, 2, 0, 1, -1, 1/2, and -2, 1/4. So you can see, again, that we're getting that exponential growth situation that curves upward and stays right close to that x-axis. Now, if I said again, graph the inverse, well, most people would say all I have to do is flip-flop x and y. But if we do that with our equation, we would have x equals 2 to the y. We would have the same problem we had with the equation when we had base 10. And that was, if you remember, we cannot just write this with y equals. So my question is, how do we write this with y equals? And so y equals, I can't undo that. What power or what root undoes the y power? So our best bet is to go ahead and graph the points as yx, which would be the inverse, even though we can't write the equation. So what we're seeing, going down there, we would have 4, 2, 2, 1, 1, 0, 1/2, -1, and 1/4, even tighter to that y-axis, -2. So you are seeing that pattern that takes us tight along the y-axis, up and curves out. And these two graphs are really inverses of each other. And again, those of you that know about the reflection idea or use that as your test for inverses, here are your values that would be on that line, y equals x. And so you can sort of see these are inverses of each other, flipped reflection images over the y equals x axis. So our problem again is we can't write that equation. So if what we did with base 10 worked, we should be able to do that same thing with base 2. So you can see it here. Even though we're not using base 10, we can go right here and say whatever our base is, raised to the power equals m, we should be able to write it as a log form. And again, read the same way. So n is the log of m to base b. The log of m in base b, or if you're reading it for meaning, n is the exponent of the number m in base b. So down below you'll see again I have exponential form and logarithmic form. If you would do, in your head or with a calculator, 3 to the 5th, you would get 243. So that's a true statement. And if we write it in log form, we're going to get the log of 243 in base 3, subscript again, is equal to 5. And so we read it as the exponent for the number 243 in base 3 is 5. And remember, if you are so choosing, you could have it written as the log of 243 in base 3 equals 5, and the 5 is on the right-hand side versus the left. It's just like an equation, a regular equation. You could have answer on the left or answer in front. So if I said 21 equals 3x, most of you know that 3x equals 21. So we got that flip-flop reflexive idea, they have to still be equal. Okay, so if that mirrors, then we should be able to go write each of the following in logarithmic form. So if these are true exponential equations, you should be able to write them logarithmically. So take a second, hit pause, write them out, and we will then share answers. If you did them fairly quickly, you should have the following. On 8 to the negative second equals 1/64. You should have had the log of 1/64 in base 8, make sure 8 is a subscript, equals -2. On the second one, the log of 2 in base 8 equals 1/3. And lastly, the log of 64 in base 2 equals 6. So our goal here was to be able to write exponential into log form, and then obviously now log form into exponential. So let's try some of those. Here they are, a little bigger. So I have log form, and again, right away you can tell it's log form because of the LOG. There's no way you're not going to have an LOG if it's not log form. So if we're trying to write exponentially, we want to get rid of that LOG and rewrite it. So again, place this on pause for a second. Write your 3 log forms out into exponential forms. So having done that fairly accurately and hopefully fairly quickly, check it. Did you get, for the first one, 4 to the third equals 64. Second one, 5 to the negative third equals 1 over 125. I keep the fractions that are in there originally, don't switch it. And lastly, did you get 7 to the 1/4 equals that 1.63? Now, that's the only one that's not a whole number, but we're just trying to show you that these don't have to necessarily be whole number exponents. They could be our roots, because remember that this statement in exponent form is really 7 with the 4th root, if we wanted to say that. So we could say the 4th root of 7 is approximately 1.63. So however you want to slice it, if you like exponent form or radical form, when they have those fractional ones, think of the roots that we were doing. Roots and powers. All right, what's left? What now is we do not have everything there. We have that missing piece. So it really makes sense to read it for meaning, and if you do, great, and you can write the answer. Or if you have to rewrite it in exponent form, there's no harm in doing that either. So reading for meaning here, the exponent for the number 81 in base 9 would put some of you at thinking at this level. Well, I got 9 to what power equals 81? Okay? If you can answer that question, then you've answered what the equal to part is. Next one, what's the exponent for the number 27 if I'm in base 9? So in this case, you got to be a little more tricky. We've got 9 to the what power equals 27. And so you should know by a couple of things we've done that we have different bases, and 9 to the first is 9, 9 to the second is 81. So you know this is really a number between 1 and 2. But here's another little trick is, if these two things aren't in the same base or power, that it'd be a good idea to write them that way. So ready? If I take 9, which is really 3 squared, okay, raise it to some other power, I have to get 27, which is 3 to the third. So look at this. If we want to get that, how are we going to get a third? You know right here, and we'll just call this an x now, that you would multiply exponents. So this makes it a little easier for you to think outside the box. If I've got 3 to the 2x has to equal 3 to the third, that's basically saying those two exponents are equal. So let's just take those two exponents, set them equal, and solve. And when we do, we get that number that we were looking for that's between 1 and 2. And we didn't have to do trial and error, guessing, anything else. Okay? So on this one, we would have had the 3/2. A little different look than you've done before, though. Okay? Now we go to the next one, third one in line. What is the exponent of 216 if I'm in base 6? So again, the brain is saying 6 to what power, because these numbers are a little bigger, equals 216. Now you could sit there and take your calculator again and say, 6 to the first is 6. 6 to the second, 36. 6 to the third, oh, is that 216? I think it is. And so you check it with your calculator and done. You don't put log in your calculator. You cannot put any of these in your calculator because they are not base 10. Okay? So they can't be done with the calculator. They have to be done paper and pencil, thinking, doing your powers of whatever your base number is. Last but not least, remember if we put a radical in it, you may want to rewrite it so it has a little different look to it. And think of that 9 in this case as 9 to the 1/2. I wouldn't turn it to square root of 9, which is 3, a whole number, because that might get you in trouble when you think about what we're doing. So, reading it, what's the exponent for the number 9? So what's the exponent for the number 9 if I'm in base 9? So 9 to the what power equals 9 to the 1/2. So what's the exponent for 9 to the 1/2 if I'm in base 9? Well, what are you noticing on this one is I have like bases. So it's sort of like one of those, duh, look at what you have. If this is your variable, x, you can see x equals 1/2. All right, from there, you should see a lot of carryover from the base 10 numbers. That's what we're looking for. That's what you're hoping you saw. If you have any questions, please bring them to class, and we will address them there.